More math for the twin paradox. It is assumed for this that you're aware of the twin paradox and that Alice stays on Earth while Bob goes to Proxima, about 4.3 light years away from Earth. More details in the other videos in this playlist. The Lorentz transformation is not about the relation between Alice and Bob, but about the relation between Alice's frame and Bob's frame, about the relation between the way that Alice sees all of space-time and the way that Bob sees all of space-time. At each point in space-time that Bob says is a given time and a given place, Alice says it has some other time and place. The conversion between Bob's designation of the time and place and Alice's is given in the Lorentz transformation. This conversion is parameterized by the velocity that Bob has in Alice's frame. Further, this is recognizable as a linear transformation, which thus has a matrix. The matrix, when written out, turns out to actually be a generic unit determinate symmetric matrix, as a quick calculation verifies. Consider what Alice's time looks like at one moment in Bob's frame over all of space in Bob's frame. Alice's time depends not only on Bob's time, but also where in Bob's frame at that time. This means that what Bob sees as a moment in history, his now, does not correspond to any now in Alice's history. They disagree on what does and does not happen at the same time. In particular, look at what Bob sees in the direction of his travel. He sees Alice's future. When Bob looks out the front, he sees the future of Alice, and when he looks out the rear, he sees the past of Alice. This worries some people because it seems then that as Bob passes Alice, he can see what is going to happen to her. It sounds like relativity makes people psychic. But this is, for better or worse, not the case. Recall that it takes time for a signal to travel. While Bob's judgment of Alice's time and place is validly given by the Lorentz transformation, Bob will not actually see this until later because of the speed of light. By the time that Bob actually sees this, by the time the light has arrived and Bob has the information, and by the time the signal gets to Alice, she will merely hear duck as she gets hit by the coconut. With that out of the way, the next issue is that the Lorentz transformation is actually not the whole deal. One needs the Poincaré transformation. The Lorentz transformation is the special case of the Poincaré transformation in which it is specified that Alice's idea of the origin of space-time, where position is zero and time is zero, is the same as Bob's idea of the origin of space-time. There is no reason at all that Bob and Alice should agree on which point in space-time is the zero of both time and space. The general Poincaré transformation has an offset in it. This is assuming only one dimension of space. The three-dimensional version also has rotations baked into it, but that is not important right now. Now look at what happens when Bob changes velocity. The slope of Alice's time in Bob's frame changes. Alice's future gets more future, and Alice's past gets more past. Yes, as Bob accelerates, Alice's clocks behind him go backward. But the same caveat as before about this not breaking causality still applies. But why should Bob and Alice still agree on where they agree? Why should not the line rotate about a different point in Bob's space? Remember that Bob could simply set his clock to daylight saving time. The actual physical location of Bob's origin of space and time is entirely a convention and has no physical significance. Clearly, since the slope of the timeline changes, there must be some point where the value of time does not change, but this choice is physically unmotivated. It is, as far as can be seen right now, completely arbitrary. And indeed, within the theory of special relativity, this really is quite arbitrary. Somehow, the pretty lights burning at the back of Bob's ship are associated with the point in space-time where Alice's time does not detach from Bob's. The one point where before and after the acceleration there is no change in the time difference. A full explanation of this is not available. It would require the as yet non-existent theory of quantum gravity. In fact, strictly, we do not even know whether this is true, as we have not done this experiment in this form. The twin paradox exercise, as typically stated, is ambiguous. To say that Bob accelerates at Proxima is not enough. One must also state that before and after the acceleration, Bob sees the same Alice time at Proxima. That if he has been looking out the window at a clock on Proxima, no change in its time would occur during the acceleration. And this means that Alice's time will change. In particular, if Bob just stopped, then Alice on Earth, as measured in Bob's frame, would leap forward in time to match the clock on Proxima. So while Alice sees Bob's time as going slowly all the time during the trip, and so Bob will be younger when they meet again, Bob sees Alice's time as moving slowly, except during acceleration, when it leaps ahead like a rabbit. This fast shift during the acceleration more than compensates for the slow rate the rest of the time, and if all these details are computed from Bob's point of view, then they agree with Alice as to who is older and by how much. And then we have the ambiguity in plain sight. The age difference when they meet again depends on who was accelerating and where the pivot point was. This information is usually left out of the statement of the problem, and without that information, the age difference is not determined.